Knowledge distillation is a technique used to transfer knowledge from a larger, more complex model to a smaller, more efficient model. This process allows the small model to achieve performance levels close to that of the large model while requiring significantly fewer resources. There are three primary types of knowledge distillation: response-based, feature-based, and relation-based distillation. Each type has its unique approach to knowledge transfer, strengths, and limitations. In response-based distillation, the student model learns to mimic the output predictions of the teacher model. This is typically done by minimizing the difference between the predicted outputs of the teacher and the student. The primary focus here is on the logits, the raw output scores before applying a softmax function, produced by the teacher model. This method is straightforward to implement since it only requires the output layer of the teacher model. Lots of pre-trained model is available for selection. While effective for many tasks, response-based distillation does not capture the internal representations or features learned by the teacher model. This can be a significant drawback for complex tasks that require nuanced decision-making or feature extraction. Feature-based distillation takes a more nuanced approach by transferring knowledge from the intermediate layers of the teacher model to the student model. This involves using the outputs of hidden layers from the teacher to guide the student in learning similar representations. By leveraging intermediate features, this method allows the student to learn more complex representations, which can lead to improved performance on tasks that require deeper understanding. Feature-based distillation has been shown to be more effective than response-based methods, especially in scenarios where the student model needs to generalize well from limited data. This method may incur higher computational costs compared to other forms of knowledge distillation because it necessitates the extraction of internal representations from the teacher model during every iteration. Furthermore, a feature-based strategy might not be appropriate for tasks where the internal representations of the teacher model do not translate or apply effectively to the student model. Relation-based distillation focuses on capturing the relationships between different inputs and their corresponding outputs. This method trains the student model to understand the relational knowledge present in the teacher model, which can include the interactions between different feature maps or the dependencies between various outputs. By learning the relationships between features, the student model can develop a more contextual understanding of the data, which is particularly beneficial for tasks like image segmentation or object detection. This approach can be more complex to implement than the other two methods, as it requires a deeper understanding of the teacher model's architecture and the relationships within its layers. This table shows the focus, knowledge source, and implementation complexity. In general, response-based distillation is the easier one, and it can be a default or baseline training method. If special requirements are needed, such as higher complexity in downstream tasks, we may consider other approaches. In summary, while response-based distillation is useful for straightforward applications, feature-based and relation-based distillation methods offer more sophisticated approaches that can significantly enhance the performance of the student model, especially in complex scenarios. The choice of method should be guided by the specific requirements of the task at hand and the computational resources available.